Hello everyone, we're at the topic of diodes, and today we're going to look at two other types of diodes that have specific applications. The diodes that we're going to study today are light emitting diodes or LEDs and the Zener diodes. Light emitting diode or LED is a type of diode that emits light when it is forward biased. To have a visible light output, the band gap of the semiconductor that is used to manufacture these diodes must be larger than that of the silicon diodes. As a result, these diodes are typically made of type 3-5 semiconductors like gallium arsenide. They have a larger VD0 compared to silicon, and their VD0 is in the range of 1.7 to 1.9 volts. The second diode type that we're going to see in this course is a Zener diode. Zener diode is a special PN junction diode that can operate both when it is forward biased and when it is reverse biased. So like a regular PN junction diode, when it is forward biased and VD reaches VD0 value, so this is VD and this is ID. So when VD is equal to VD0, the diode is going to start conducting, and in the piecewise linear model, we're going to say that the voltage drop across the diode is going to stay at a constant value equal to VD0. So unlike the regular PN junction diodes, Zener diodes can also operate in the Zener region when they are reverse biased and in the reverse breakdown region, which is this region. In that case, VD is going to be equal to negative VZ, and in piecewise linear model, we're going to assume that the voltage drop across the diode is going to be at the constant value equal to negative VZ, or the Zener voltage. And in the Zener region, the current that flows through the diode, it has a negative value. In other words, in the Zener region, the current flows in this direction in the diode. So in the labeled direction for ID, if we label the current through the diode in this direction as ID, then this ID is going to have a negative value when the Zener diode operates in the Zener region. And Zener diodes are specifically manufactured to operate in the Zener region, and they're commonly used in voltage regulators. We are going to see a simple voltage regulator circuit using a Zener diode in this video. The idea with the voltage regulator is to maintain a constant voltage across the load regardless of the changes on the supply voltage or the changes on the load current. So again, for the Zener diode, we're going to use piecewise linear model that consists of 3 lines. When the diode is on, we're going to have this line in here, and in this condition, VD is going to be equal to VD0. This is the equation for this line, and ID is going to be greater than or equal to 0. When the diode is off, I have this line in here, and in this condition, ID is equal to 0. This is the equation of this line, and VD is going to be less than VD0 but greater than negative VZ or Zener voltage. And there's going to be the third region for the Zener diode that we didn't have in the regular PN junction diodes, that is the Zener region, and we're going to represent it with this line. And in the Zener region, VD is equal to negative VZ or negative Zener voltage, and the diode also conducts in this region, and in this region ID is less than or equal to 0. So there are 3 circuit models for the Zener diode. When it is on and conducting, we can replace the Zener diode with a constant voltage drop model just like before. When it is off, we're going to replace it with an open circuit, and when it is in the Zener region, again we can replace it with a constant voltage drop model, but VD in this state is going to be equal to negative VZ. Now we can write those equations again. This time we're going to use the node voltages at 2 terminals of the Zener diode. So I'm going to label this terminal, the node voltage at this terminal, as V1, and the node voltage at the second terminal as V2. Now we're going to assume a Zener diode with VD equals to 0.7 volts and Zener voltage of 5 volts. Now, if V1 minus V2 is between 0 and 0.7 volts, the diode is forward biased, but it's not on yet, and ID is equal to 0. If V1 minus V2 or VD is between 0 and negative 5 volts, then the diode is reverse biased, but it is not in the Zener region, so it's off. Again, ID is equal to 0. When V1 minus V2 is equal to 0.7 volts, the diode is forward biased and it is on. In this condition, ID is greater than or equal to 0 and VD is a constant value equals to 0.7 volts. Now, when V1 minus V2 equals to the negative VZ or negative 5 volts, the diode is operating in the Zener region. It conducts and ID is going to be equal to or less than 0. And the voltage across the diode is going to be a constant value equal to negative 5 volts. This is an example of a voltage regulator circuit using a Zener diode, and in this problem we would like to find IL and VL when the input supply voltage is equal to 10 volts, and we want to see for what range of VS and RL values the Zener diode is going to be in the Zener region and the circuit is going to operate as a voltage regulator. Let's start by labeling the voltage across the diode as the way that we labeled it to find the piecewise linear equations for the Zener diode. And I'm going to label this as VD, and the current is going to flow in this direction. If you label the current and voltage in this way, then you can use those piecewise linear equations that we found previously for the Zener diode. And I'm going to label the current that flows through RS. This is plus minus voltage across the load. So with that, we can write the KCL for this node here. And if you do that, KCL tells me that IS that enters the node plus ID that enters the node minus IL which leaves the node is equal to 0. And I can write 1 KVL here in this loop, and that tells me that VS is going to be equal to RS times IS minus VD. Also, I can write another KVL in here, and from there I have VD plus VL equals to 0. From there, VL equals to negative VD. So these are three equations that I have for this circuit. Now, starting to solve this problem, I'm going to assume that the diode is in the Zener region and use the linear equations that I found for the diode operating in the Zener region. So assume that diode is in the Zener region. So the two equations that I have for the diode operating in the Zener region are VD is a constant value equal to negative VZ, and ID is going to be equal to or less than 0. So ID is going to have a negative value in the direction that I labeled in the circuit. If VD is a constant value equal to negative VZ, then I know the value of VL here. From there, VL is going to be equal to, because I already found out that VL is equal to negative VD, then from there I can write VL equals to VZ. And in this circuit, for this diode, VZ is given as 3 volts. So voltage across the load is equal to 3 volts. Good. Now I need to find IL and IS. IL, I can find it using Ohm's law, because IL equals to VL divided by RL. That is going to be equal to 3 volts divided by 1K. That's going to give me 3 milliamps for IL. So IL equals to 3 milliamps. Now, using the KVL that I found for the main loop here, using this KVL in here, I can find IS as well. And for that, I have IS equals to VS plus VD divided by RS. And I know the value of VS, I know the value of VD, and I also know the value of RS. So I can find I sub S in this circuit. VS is equal to 10 volts and VD is equal to negative VZ, because I assume that the diode operates in the Zener region. That's going to be negative 3 volts. And from there, VD is equal to negative VZ, and VZ is 3 volts, so I have 10 volts minus 3 volts divided by RS. RS is equal to 1 kilo ohm. From there, IS is equal to 7 milliamps. Now I only need to find ID and check it with my assumption, check it with this one because I assumed that the diode operates in the Zener region. As a result, I had one inequality. The inequality is ID is less than or equal to 0. After finding ID, I need to check it with this inequality and make sure that it holds. Otherwise, my assumption was incorrect. So ID is going to be equal to, using the KCL that I had in here, ID is going to be equal to IL minus IS. That's going to be 3 milliamps minus 7 milliamps. That's going to be equal to negative 4 milliamp. This is less than 0, so my assumption for the diode operating in the Zener region was correct. And these are the currents in the circuit. And I found IL and VL for the circuit as the question asks us to do. In the second step, I need to find the range of VS and RL for which the diode is going to operate in the Zener region. So it's going to function as a voltage regulator. So I expect in a voltage regulator, the voltage across the load is going to be a constant voltage value regardless of the changes on VS or the changes on the load resistance value, or correspondingly the changes on the load current or the current that we draw from the voltage supply or the regulator. To find the range of RL or VS, to make sure that the diode operates in the Zener region or maintain the diode operation in the Zener region, I can use the inequality for the current through the diode when the diode operates in the Zener region. That is, when the diode is in the Zener region, the current through it, in the way that we label it, is going to be a negative value. Using the KCL equation that I found before, I know that ID is equal to IL minus IS, and that is less than or equal to 0 when the diode is in the Zener region. From there, IS is going to be greater than or equal to IL. Now, when the diode is in the Zener region, VL is equal to VZ, we found it, and IL is equal to VL over R V sub L over R sub L, and that's going to be equal to VZ divided by RL. On the other hand, IS, using the KVL that we wrote before, IS is equal to VS minus VZ divided by RS. So I have the equation for IL and I have the equation for IS, and I'm going to use this inequality to find the range of VS when RL is constant and the range of RL when VS is a constant value. So let's do that. I have VS minus VZ over RS must be greater than or equal to VZ over RL. Let's first assume that RL has a constant value and we want to find the range of VS that keeps the diode in the Zener region. From there, VS over RS is going to be greater than or equal to VZ multiplied by 1 over RL plus 1 over RS. From there, VS must be greater than or equal to VZ multiplied by 1 plus RS over RL. As long as VS is greater than this quantity, the voltage across the load is going to stay at a constant value equal to VZ, or the Zener voltage of the Zener diode. So that the variation on VS is not going to affect the load voltage. We can also use this inequality that we derived in here to find the range of load resistances or the range of RL values for which the voltage across the load is going to stay at a constant value of VZ. And if we do that, we can write this inequality as dividing both sides by VZ. I'm going to have VS over VZ minus 1 divided by RS is greater than or equal to 1 over RL. From there, RL is greater than or equal to RS divided by VS over VZ minus 1. So as long as my load resistance value is greater than this quantity, then the voltage across the load is going to stay at a constant value equal to Vz, and the only thing that happens while our load is increasing is that I load is going to decrease, and it's going to maintain a constant voltage drop across the load. So it's going to act like a voltage reference. Thank you for watching.